everybody. This is Bill Bittner, and today is Monday, March 16th, 2020. With us today, we have Jacob Gagnon from the ZVM Development Organization, and he's going to talk to us about single system image. Jacob, I'll turn it over to you.
All right. Thank you, Bill. But as Bill said, we're going to be covering part one of what will be a three-part series on ZVM single system imaging, or SSI for short. And it's really going to expand upon the very brief introduction we had to it all the way back in our virtualization basics session. I know this says configuration and setup, but I want to set the stage right. So I won't be showing you the detailed steps and walking you through all that you need to set up an SSI, but I'll be talking about the key aspects of the environment, the attributes that go into it, and through that you'll see all the components that go into configuration and setup. But we won't actually be going through that actual exercise today. It's really going to set the stage for parts 2 and 3 of this series. So this is kind of the structure that I want to take for today's session. We'll start by first reminding ourselves of the basics, right? What is SSI? What is LGR? Why might this all be useful to us in the ZVM space? And then we'll spend the majority of our time, like I said, on the major aspects of an SSI cluster and really what makes it tick. And if we have time, we'll wrap up with a brief overview of cluster management. So with that, SSI, what is it, right? It's our solution in ZVM to multi-system clustering and management. It is newly free, and so what I mean by that is prior to ZVM 7.1, it was a priced feature of ZVM, and with 7.1, we removed that price tag, right? So that you could play around with it without having to worry about breaking out your wallet. Now, sometimes I will hear people draw the comparison of SSI to the concept of a ZOS sysplex, but I want to caution us against doing that because outside of them both being clustering technologies, everything beyond that's more like comparing apples to oranges. Right? And so I think we can probably only add to our confusion by trying to take this concept of a sysplex and map it to ZVM. We're just going to talk about ZVM today. So SSI allows us to take up to 4 ZVM instances and combine them into a single SSI cluster. Now they can be different LPARs on the same CAC, or they can be 4 entirely different CACs, or any combination in between. Right? Now I've got a whole chart on the key advantages of SSI, but really what this allows us to have is a set of shared resources among a cluster of ZVM systems, which makes management of the multi-VM environments easier. It makes resource allocation and management easier. And it actually enables us the ability to move a live running Linux guest from one VM instance to another without taking an outage to our guests. So that function, which we call live guest relocation, or LGR, is going to be the real center topic for part 2 of our SSI discussion. So when we talk about the resources that are shared between members of an SSI, what do we really mean? Well, we primarily mean shared disks for any of the data that we use, both by CP to manage our individual ZVM hypervisor or the data that's used by our virtual servers themselves. We also mean things that are needed for common network access among our cluster. We'll really dive deep into what all this looks like today. Now, to achieve this clustering and sharing, one of the key things that we need is the ability to talk with members of our cluster. So that is done by making sure that all members are part of the same ISFC collection. I know we love acronyms in IBM, so ISFC is another one in the toolbox. It stands for Inter-System Facility for Communication. Basically what it means is that we have to have channel-to-channel or CTC connections from each system to each other system so that we can talk to whoever we need to. A ZVM control program's job is to use these CTC connections, validate and manage all the resource and data sharing across the cluster. We achieve that with a messaging protocol over the ISFC connections. Now, this is cool because it means that we can do this management of clustering by CP and CP alone. In other words, we don't need a special server or an arbitrator or anything like that to make this work. We can completely manage it within CP. So that's very beneficial from a reliability and a maintenance perspective. So this is kind of my chart on the advantages. It comes in a variety of different ways, right? So Right off the bat, what SSI helps us with is the avoidance of server sprawl. In other words, we have a growing number of VM servers, which will become overly cumbersome to manage by a single system administrator. So if we only have to manage one cluster, it's easier than having to manage 4 individual systems. Outside of that reduced management cost, ability to handle and manage planned outages without significant disruption to the workloads that our guests are running. Right? And so this, again, is all about LGR and live guest relocation. The idea that we can offload workload, Linux workload, from one member of our cluster to another member of the same cluster, which lets us do any software or hardware maintenance that we need to without taking an outage to our guests. The other thing that we've seen SSI used for, and we've seen clients use this, and we use this in our own development as well, is to simplify and manage the testing of new workloads and testing of environments. One of the advantages of SSI is that we can have different hardware and software levels and different combinations of them. Right? So we can test out workloads in the variety of combinations of environments we can think of before we move those workloads into production. And in the lab, we use it to test out the ZVM product with a variety of different hardware and software levels. So we also see it as a robust testing environment as well. Okay, so it's always dangerous, I think, to walk blindly into something without understanding the big considerations, and SSI is no different. So a couple things to be aware of before you go and start playing with it, right? First of all, there are, of course, the physical considerations of where our systems are physically located with respect to one another and to the shared resources that we need for the cluster. Now, these limitations and considerations aren't anything new. They've always been. Right? Basically, what we mean by this is that we need cables long enough to connect our systems together, to be able to connect to our DASD, to be able to connect to our network devices and things of that nature. And so those are pretty strictly defined and nothing new. But a couple less obvious considerations for us to be aware of. First of all, the installation can't be to SCSI devices. SCSI is a fixed block architecture, and our install process doesn't support that. So we just can't install the SCSI. Now, this, of course, doesn't mean you can't use SCSI in your systems. For guest use, you can. Right? And I'm sure over the last several sessions, you've seen reference to SCSI in a ZVM context. And so that's fine, right? We just can't install to them. Also, if you're using RACF in a cluster, it's got to be on a full pack 3390 volume. And that's because the database has to be shared to all members of the cluster. One thing to consider here is that if you configure both a primary and a backup database for redundancy, right, then they each need to be a full pack volume. So just keep that in mind as you're planning. And as I hinted before, we only support LGR for Linux guests VM, so you can't relocate ZOS guests or TPF guests or anything like that. We only support it for Linux.
Jacob, the other thing we might want to point out is that the other requirement for ECKD, so the other thing that can't be on FCP SCSI is the persistent data record area, or the PDR. I know we haven't talked about that yet, but that's the other reason for other area besides RACF that would have a requirement for ECKD.
Okay, yes, thank you, Bill. That's a good point. And PDR, you're going to hear that term float around a couple times before I actually get to breaking that down, but we will talk about that more. But thank you, Bill. All right, live guest relocation. Again, we'll break this down a lot next week, but LGR and SSI go hand in hand, so we do have to talk about it a little bit now. Okay, so we talked about the moving of workload with LGR for maintenance, but another reason that we might move around workload is to just get better overall balancing across an SSI. But the idea is that we can relocate guests that are getting throttled on one very busy system, kind of move and spread the workload around to kind of get that better balancing. The actual relocation itself is done with the VM relocate command, which has a lot of different flavors to it, and we can do a lot with it. And so we can do things like test out if relocation is going to work, right? We can check the status of relocation currently in progress. We can actually modify the parameters by which a relocation in progress operates. We can cancel a relocation. All sorts of commands that are at our disposal, all centered around VM relocate. But one thing to keep in mind here is that relocation is a manual process. It's something that we have to actively decide to do. we as the administrators, not CP, right? CP doesn't automate this at all or make the decision of when and how to do a relocation. But we'll dissect that a lot more next week.
Jacob,
Yep.
about the last chart when you were saying that the systems need to be close enough to be connected by PyCon CTCs, I was wondering if they are on the same box. Could you do these connections using HyperSocket, for example, or no, if they need to be physical connections?
So you can set up logical CTC connections. Bill, maybe you have a better idea of the HyperSockets portion of that, but certainly you can set up logical CTC connections if you're in the same CAC. Bill, you want to take that one?
So the ISFC, so the communication vehicle that Jacob mentioned earlier, that we use for the management aspect, currently limited to CTCs only. So they can be, shared channels and things of that nature, but they still have to be CTCs, and therefore HyperSockets. Also, we get asked sometimes about coupling facility. Neither of those is eligible for this.
Okay, thank you.
All right. So I think the key bit, one more thing about live guest relocation that we need to understand for part one is that it's not a free process, right? So we need to make sure at the end of the day that whatever the destination member is that we're relocating to has enough resource capacity to handle the overhead of relocation and to run our guest effectively. One aspect of this that we also need to be aware of is that we need to make sure our target member has at least as much capability as the member we're currently running on. Now, what do I mean by capability? Right. Well, when we have software and hardware running at the latest levels, right, we have a certain amount of capability we can run, a certain amount of function that's provided with the hardware that's enabled by the software. And so once we tell a guest that he can have something, they can use a facility on the hardware, we can't take that away when we relocate. So capability is something that we're going to see a lot next week. One analogy that I kind of use to put this into perspective for myself is to go back to the wonderful dog that I have. He brings me a lot of joy and happiness. And so sometimes I like to reward him with a rawhide to enjoy. And I'll tell you, he really, really loves rawhides. Now, once I give him one, I can't take it away. Because if I do, he turns into a hellhound out for blood. And I think he's actually drawn some blood on me a couple of times when I try to take it away. Right? So just like I can't take a rawhide away from him once it's already been given, can't downgrade a guest capability once he's already been told that he has it. And finally, we do also have to make sure that if our guest is using any resource on the source side member, it has to be available on the target and destination member as well. We'll dive into a lot of this next week. So for now, let's break down the major attributes of our SSI cluster. In order to do that, I like to show this overall picture of what a general SSI kind of looks like, so we can kind of refer back to this mental picture as we begin to break it down. So one thing we see is that each of our four members has some shared volumes, you see in the center of this graphic, and these hold some very important housekeeping information, as well as any of that shared data that we need for relocations or anything like that. But not everything needs to be shared in an SSI, right? So each member can also have its set of local information in DASD volumes as well. We see the CTC connections, right? That can be logical or physical connections, depending if you're inner CAC or outside the CAC. And that forms our ISFC cluster. And then we also see that kind of dotted circle around that forms the common LAN segment for guest IP communications. The first major attribute that we'll talk about is right at the beginning with installation. Right now, when you go through the installation procedure, you can actually create an SSI cluster without having to do multiple system installations. In other words, if you're setting up a 4-member cluster, you don't have to do 4 separate installations. You can instead provide on the install panel all the information that you need for cluster definition, including the names of our members, names of the LPARs where our systems will be IPL'd, information about our DASD and the CTC configurations, all that good stuff. And the install process will actually install the VM images and provide a couple things for us: a common system configuration file, a common source directory, which we'll talk about individually as well. Now, the install process is all about flexibility, though. Okay, so you don't have to do a full SSI installation right off the bat. Okay? Maybe you want to configure for more members, and you'll be installing from day one. So let's first talk about the case where you actually want to do a non-SSI installation. Right? The install process is still going to define the system config, the directory, the DASD layout, all that stuff in a compatible way. So that if later on you decide, well, yeah, maybe I do want to use SSI, and it'll make conversion to an SSI a lot easier. Now, if you wanted to create a cluster that had more members than you're actually going to be activating from day one, let's say you want to define for 4 members, even though you're only going to bring up 2 right now, that's fine. You can do that. And the install process will kind of create placeholders for the 3rd and 4th members and let you activate those images whenever you're ready to bring them online. There's a lot of flexibility in the install process when it comes to SSI to make sure that the transition to using SSI and the transition to having more members on that SSI are as smooth as possible. The next couple of slides are going to talk to an attribute of SSI that is the backbone for what we call a single maintenance stream. Now, before I get into what that really means and how that maintenance stream looks, we need to understand the basic organization of DASD volumes and minidisks in an SSI. Okay, so first thing we see on this chart are our cluster-wide disks, right? So starting with the common volume, VM COM1, this is actually the default name I think we give it. This is where we have the shared data files for our SSI cluster. Things like the SSI PDR, persistent data record, and we'll talk about what that means in a little bit. The shared mini disks that are owned by the pmate user ID. These are the disks that have that common system config that I talked about, our source directory, and then the VM says E inventory disk, which is going to be very important and required for install and service purposes. Okay. And then we see a second set of shared mini disks for each release in our cluster. So this is where service for each of our releases is actually loaded and managed. And that's at the bottom middle, right, with the 640 RL1. So in this case, that would hold everything for 640. But if we had a mixture of 6.4 and 7.1 systems, for example, then there'd be a whole nother disk for 7.1 that has the same stuff. And that's for servicing the 7.1 members. We then have our system volumes for each member, so that you can see those on your chart as M01 res and M02 res. These are member specific and not shared, right? So these have the warm start and checkpoint areas for each member, the object directory, our standard system mini disks, so those types of things. We also see the paging volumes. Paging volumes are also member specific and not shared. So you can't share paging in an SSI. And then spool is a little bit different because you actually have to share a spool in SSI. And I break down spool as a whole separate attribute. So we'll kind of talk about what that means in a little bit here. But all that kind of sets the stage for what we mean when we say single maintenance stream. So for each release in a cluster, there are a set of service mini disks that are managed by a maintenance user ID. And that naming convention is usually maint and then whatever the release identifier is. So for this example, 710, and you can see that in the top right-hand portion of your screen. So each member now in the cluster will have separate production disks, which actually lets us push service into production for each of the members individually. We're ready to do that. We follow a pretty simple process, right? First, we log on to, in this case, maint 710 on any member, and then we run the service command to install whatever RSU or core that we're looking to apply. Then we will log on to the maint 710 ID on the specific member where we want the service applied. We'll issue put to prod, which will push the service changes to the appropriate production disks for that member. Right? And so this lets us manage each of the individual members through kind of one maintenance stream. And so that's why we call it the single maintenance stream. Okay, so remember, on our shared cluster-wide disks, we have a shared system configuration file. So how, with a single system config for all members, do we tailor that specific that file to the specific needs of our individual systems? So we actually achieve that with something that we call member-specific record qualifiers. Okay, so the first record in the config is a series of system identifier statements, which is going to denote the members of our cluster and which LPARs they're going to be brought up in. Now, one thing you can do is optionally set the system name to actually be the LPAR name if you want to. But at the end of the day, the system name defined here is going to be what's used as that member-specific record qualifier that we'll use it to tailor the rest of the file for each of our guests. And we'll get into what that looks like on the next couple slides. The other thing that we see in our config file is the definition of our cluster configuration, right? So this denotes what volume is going to have our PDR. It defines which slots will be occupied by which systems. And so very important aspect that we need, absolutely need for coming up in an SSI. Now, also in the config file, we define our IS links, again, the CTC connections between the member that we're defining for and each other member of the configuration. And so you can see the record qualifier that I was talking about. And that's denoted here by the begin and end tags. So in this case, these three activate IS link statements will be run on VM-sys1, right? And it defines CTC connections to each other member of the cluster, so to members 2, 3, and 4. Right? Of course, we also define our CPU-owned volumes, be them shared or private, as per our usual system config practice, and we'll look at that in a little more detail here now. So again, because this is a shared config file, to define a non-shared volume for a specific member, you need to start it with a record qualifier of that system name that we defined at the top of the file. So we'll do this for our sysres volumes. We'll do it for paging and tdisk, which I'll show you in the next slide. And so you'll notice here that there are some common volumes, the spool volumes mainly. And those aren't qualified to a specific member because they have to be shared. Again, I'll have a whole thing on spool, but for now, just know that they have to be defined for everybody, right? They have to be shared. This chart shows us that paging and tdisk volumes in our config. And the thing that I want to note here is that unlike the spool and the dump volume definitions, we'll actually define the page and tdisk starting in slot 255, right, which is the maximum number of CPU-owned slots we can have, and then working our way backwards. We actually do this to avoid any conflicts with the shared spool dump volumes, because that's when we start to get into corruption territory if we kind of infringe on that territory. So we'll start from the back and kind of work our way towards the front with those volumes. All right, so here's where we get to actually learn about what we mean when we say PDR. So what is it? It's a very important shared construct, right, among all the members of our cluster, and it contains important information about really the state that each member in the cluster is in. At the end of the day, it's a serialization point, and that's the best way to think about it. It's used to track the state of affairs. And so one thing that we do is we make sure that our member tracking is meaningful and accurate. So what happens is that we have each member in the cluster periodically provide and receive from other members what we call a PDR heartbeat. And what a PDR heartbeat is essentially a timestamp metric for us to make sure that everyone is still alive and kicking in the cluster. Right? So if for some reason a member becomes unresponsive, we'll know about it because when we go to write our heartbeat to the PDR, we'll look for everybody else's heartbeat. We don't see somebody, then no heartbeat means no bueno, right? So that's not good. And so that's kind of how we make sure that the cluster is staying healthy. Now, the PDR is created and monitored through the utility that we call form SSI. There's only one PDR for the whole cluster. One thing that we can do, though, is move the PDR around if we need to with the form SSI utility. So if we need to move it to be on a different volume, we can do that to kind of help maintain that. So yeah, that is the PDR in a nutshell. And actually, like I said, more in the chart. So if you do a form SSI display, This is the kind of information that we keep in the PDR. And we do keep a lot more information as well that CP uses to kind of manage everything. But this is the important stuff from an end user perspective. Right? So you can see that time-stamped heartbeat that I talked about. For each system, you can see the status. So in this case, we have a 4-member cluster. 2 members are joined. The 3rd member is in the process of joining, and the 4th member is down. So this is how you can actually see that PDR information. Now, as careful as we are with the shared system configuration file, we need to be very careful that we don't, on one instance of CP, allocate any warm start, checkpoint, spool, paging, T-disk, or directory data on a volume that's owned by another member. So that's when we start to tread on corruption territory, right? So one thing that we need to do for each CP-owned volume is mark it with ownership information. And that information is really just like a luggage tag in that it identifies the name of the cluster that owns it, the name of the system that owns it, and it lets us kind of respect that information and not lose track of it. If you want to actually see that information, see that ownership information, then there's a query for it, query CP-owned command. And that'll show you just what I said, right? What cluster owns each volume, what members of that cluster own which volume. And so you get all that ownership information from that. So the next attribute we'll talk about is the user directory. Again, this is a shared directory. However, you do need to run directxa on each member to apply it, right? Now, the benefit to the shared directory construct is that the object directories that get created are identical on each system and on each user. And so each user is guaranteed to have the same access rights and privileges and definitions, regardless of which member they're actually running on. And so that's very important when we start talking about LGR, because it wouldn't be good if we had, one definition of a user that differed from member to member. Now, there are 2 types of virtual machine definitions that we can have in that user directory and that we need to be aware of. So first is the traditional virtual machine or the user statements, right? These users can be logged on to any member of the cluster, but the key is they can only be logged on to one member at a time, right? So like I said, this is a traditional type of virtual machine. It's used for our general workloads, users and applications. It's used as platforms for running guest operating systems, service virtual machines, and really any server that requires only a single logon to the cluster. Now, to contrast that, the other type of machine that we can have are multi-configuration, or what we'll sometimes abbreviate as ident virtual machines. And these machines can be logged on to multiple members concurrently, right? Now, the instances of an ident user can have common attributes, which are defined just under the identity statement. And so these will be run and defined no matter where that ident user has come up, no matter which member he's on. But since the ident user can be logged on to multiple members concurrently, we can actually tailor and configure access to different resources based upon which member they're actually on. And that's achieved via creating subconfiguration statements under the identity statement. Now, ident machines are used for system support IDs, like maint, for example. And so this allows maint to perform various tasks on a member without needing to have to log off of one machine and then log on to another. It's also used for certain service virtual machines and servers that need to be running on each member of the cluster. A good example of that would be TCP/IP. You do need to have an instance running on each member, and so TCP/IP is configured as an identity user as well. All right, so let's talk about spool now. We mentioned them, and I mentioned that they do need to be shared, right? And why do they need to be shared, right? Well, spool files need to be accessed on any member of the cluster, regardless of where they were created, because a user needs to be able to access their files, even if they've moved around the cluster, right? Now, one thing that I want to remind us of here, or maybe for those that haven't heard this, inform of, is that there is a limit on the number of spool files that you can have. for every user, and that's normally 9,999, right? So just shy of 10,000. That's for a non-SSI environment. In an SSI, this gets cut by 4, and we do this so that cross-system spooling can work. So that basically each member of the cluster can carve up or create a certain number of spool files for a user, but then you can access them from wherever, and they can be manipulated from wherever. Now, this is a statement for standard users, for single configuration virtual machines. Ident users, they cannot participate in cross-system spool. In fact, they can only access the spool files that were created on the member that they're currently running on. So to get around that, there are spool transfer services. So like RSCS can actually transfer files from one member to wherever the ident users reside, and so that way they can access it. But cross-system spool only works for the single configuration virtual machines. Thing that we have is something called the Single Console Image Facility, or SCIF, as you might hear for short, and that as well can be cross-system. The facility allows one virtual machine that we call the secondary user to monitor and control another virtual machine that we'll call the primary user. Now, if you ask me, maybe this is just because the wires are connected differently in my brain, but that seems kind of backwards to me. It seems that the primary one would be the one I'm on, and then the secondary one would be the one I'm controlling, but that's not the case. It's flipped. So try to keep that straight in your brain, right? So if both the primary and secondary users are standard single config virtual machines, then it does not matter where the users are in the cluster. They can be on the same member, they can be on different members. Everything will work as expected. That's the whole cross-system part of the SCIF. But just like spool, if we're talking about ident users, then the SCIF facility is only going to work if both machines are on the same member, right? So you'll find that that's a common theme between the single config and the multi-config virtual machines, that the single config, this cross-system capability is there, and for a lot of the cases, that's not the case for the ident users. Okay, cross-system CP commands. So we can use the @ command to issue most privileged commands to CP, and we do that by specifying the system name that we want to target, and then the command that we want to issue. Likewise, we have an @sysname operand on a variety of different commands, which can also let you target specific virtual machines on different active members. So for example, let's say I wanted to message a user ID that's currently on a different member of the cluster. I could say message, whatever user ID I was trying to reach, the @ operand, and then the system name of the member where they're located. And so we have some capability of doing CP commands across the system as well. Okay, a few more charts and attributes to discuss, but I think we're making good progress here. So as we noted earlier, minidisks can be shared across the cluster or restricted to a single member. Okay, so how do we actually manage that management across the cluster? Well, when we issue a link command, right, the members of the cluster will exchange information to determine who has access to the minidisk and kind of make sure that no conflicts exist. Now, one of the caveats here is that the conflict resolution that CP does will only hold water if the minidisk is exclusive to this cluster. But technically speaking, you can share a minidisk outside of a cluster. But if you do that, first of all, we don't recommend it. And we don't recommend it because CP can not automatically manage link conflicts at that point, right? The other thing there is that if you share a minidisk outside the cluster, then it's not eligible for minidisk caching, and so you don't get that benefit. So though I've said that you can technically do it, I don't encourage it. And certainly you're going to find in an SSI environment that you lose a lot more than you would possibly gain. So if we hold to that suggested recommendation of keeping everything within the cluster, then CP is going to handle all the link conflicts as well as allow for the minidisk caching on the volume whenever a write link is established. If anyone is familiar with the virtual reserve release support, essentially that is just a way for DASD volumes, which are shared among strictly ZVM guests to have the serialization and reserve release functions managed by CP, not the hardware, is supported across members for full pack mini disks. All right, so what does that mini disk cache management look like? Here's a little graphic to kind of help us out. So whenever we have a member that gets a write link to a mini disk, in this case, member 2 will be trying to get a write link, then what we'll do is we'll stop using mini disk cache on all other members. Now, in this graphic, just to kind of keep the chart organized, it's just a 2-member cluster, right? So this means that on member 1, we're going to stop using mini disk cache. And we do that so that we're not providing any obsolete data to any guest with a read-only link. That would be counterintuitive and counterproductive to what we're trying to do here. So member 2 would then do whatever it needs to do with the write link. And whenever that write link is released, we can then reinstantiate mini disk cache on the read-only members, and everything will be golden and good to go until the next time somebody wants to get a write link. All right, so that's mini disks. But how do we make sure that the real device that one member is talking about is the same real device that another member is talking about? So ZVM provides a way of uniquely identifying real devices so that we can ensure that members of a cluster are in fact using the same real device or talking about the same real device. And we do that by generating what we call an equivalency identifier, or you'll hear it called ECID for short. And so an ECID is unique on a member level, right? Because no other device within a member should have the same ECID. That's the unique part. But it's going to be the same from member to member, right? Because we want each member to agree on what a real device actually is. So CP is going to do that for devices that uniquely identify themselves, like disk volumes and tape drives. Some other devices, though, like network adapters, CTCs, OSA adapters, we need more information to make a unique identifier. Things like access rights to a specific device or a particular network fabric that we're connected to. So for those devices, we can actually define a unique ECID using the set rdevice command. Right now, ECIDs are very important for LGR, again, because we need to make sure that what we need is available on the destination member. And so we'll use ECIDs internal to CP to make sure and test out that a relocation is actually good to happen. And we'll kind of wrap up the attribute talk with virtual network management. So pretty straightforward here. The assignment of Ethernet and MAC addresses is coordinated across an SSI. Members of a cluster will talk with each other and ensure that a MAC address is not already in use by another member. When we relocate a guest, what this means that we will also relocate his MAC address, so his MAC address goes with him. The other big thing from a virtual network side is that each member of a cluster at the end of the day needs to have identical network connectivity. Go back to that picture that we had, right? It's got to have that common network fabric going around the whole cluster. Because of this, we need to make sure that the vSwitches have the same name on each member, and that each member's vSwitch is also connected to the same physical LAN segment. And that can be assured by ECID assignments for those devices. All right, so just a few words on SSI cluster management. And this is really just to get our feet wet. So to kind of look at what happens at join and leave time. So when a member wants to join the SSI cluster at IPL time, a couple things happen. The first step is that CP needs to verify that the configuration is actually compatible with the cluster. If he passes that, then the second step is that the member is going to establish communication with all the other members. This is the process that we call the join process. So if we look at code snippet here, you can see what that looks like, right? So we see that we have a member, JFSSI able 2, and they are coming out of the cluster. So once we register that the member is joining, we're going to put the cluster into a state that we call influx. Right now, what's that influx state really do, and what's it mean? Basically, what it means is that we don't really know who's part of the communication right now. You know, things are exactly as it says, in flux. And so CP will know that when we're in the influx state, that we need to halt anything that requires cluster stability So certain messages won't go out, certain things will kind of be locked down while we're in this influx state. Now, once we verify all that we need to verify, we can mark JF SSI able to as joined. Then we'll ask all other members if we're ready to then go back from the influx state to a stable state. If we are, we do so, and then our member has successfully joined the cluster and can participate in communication. On shutdown, it's a very similar story. We'll mark the member as leaving. And again, we'll put the cluster in the same influx state so that CP doesn't do anything it shouldn't. And then once the member registers as down, we'll communicate with the remaining up members and see if we can return to that stable state and resume normal operation. Okay, so under normal operation, all of our members are communicating and sharing happily. Okay, so as guests are running, CP is constantly policing things, making sure that our volume ownership markings are good to go, that our minidisk accesses are happening as they should and not happening if they shouldn't, right? For non-ident users, we're making sure that there's only one instance of VM running in the cluster at a time. But sometimes things go wrong, and primarily that manifests itself when we have a member who fails to communicate. Right? Again, we detect that because the heartbeat for that member will have gone away. And so if that happens, then we'll put the cluster into another mode that we call safe mode. Safe mode in this cluster means that existing workloads can still continue to run, but we're not going to allow any relocations during this time. We're not going to have any new accesses to shared resources, and we're going to put everything on hold that we need to until the failure is resolved. It's no different from booting a Windows machine in safe mode or booting your mobile device in safe mode or anything like that. It pretty much locks down things that would not be safe to do while allowing you to continue to do the things that are safe. Now, in most cases, the failures that happen in SSI that would cause this are minor hiccups or blips that'll work themselves out naturally. But if we do need to have some manual intervention, there are a couple of things that we can do there. We have a command called set SSI member name down, and that will try to force a problem member out of the communication so that the remaining non-problematic users can get back into a stable state. We also have a repair IPL parm, which can be used to bypass SSI cluster initialization and management tasks at IPL time. Very similar to what no autolog would do if there was a problem user, right? So it essentially bypasses what would be problematic. But that's pretty much the end of my prepared remarks, right? Hopefully that's giving you a better overview of everything SSI. It's a very, very powerful tool in the VM toolbox. But again, this is just half the story and probably not even half, right? Next week, we'll tackle the LGR, and we can see in the following week some performance considerations for SSI and all that good stuff. But thank you all for taking the time and listening to me for the last hour or so.
All right. Well, thank you very much, Jake.
You're welcome.
Everybody have a great day and a good week. Talk to you later.
Thanks for watching. If you enjoyed this video, don't forget to like and subscribe to see more videos like this one. Have a suggestion for another video topic? Feel free to leave a comment below.